Great, welcome back to 10.4.18.6.18. Today we're going to be moving beyond Monte Carlo methods to Markov chain Monte Carlo methods. And the idea is that we're still going to be trying to draw samples from distributions, but we're going to be relying on some slightly different mechanisms to actually pull that off. As well, as soon as we get into Gibbs sampling, we'll start to see sort of some immediate applications to inference on models like factor graphs, where we might want to use these. Okay. So homework 3 is out. So someone had asked a good question of, why don't we have a full 2 weeks on this assignment? The reason for that was, we basically are trying to keep homework 3, 4, and 5 a little bit shorter than homeworks 1 and 2. If that doesn't happen on homework 3, you should come and complain loudly to me, so that we really know. Though, I mean, we're actually really using the hours spent that you report at the end of each homework and trying to track how much time you guys are spending. So definitely continue filling that out. And then as well, we do have a recitation that I didn't put up here, but we have a recitation today at 6:30 p.m. in Rashid Auditorium, GHC 4401. That's the big lecture hall. So we encourage you to join for that. And then project team formation. So this is an important milestone, but in some sense, it kind of goes hand in hand with the actual project proposal that isn't due for another maybe 2 weeks. So the actual milestone for project team formation will be that we want everyone to correctly submit basically just their names in a PDF to Gradescope using the team functionality of Gradescope. So there's just like enough trickiness here that we want to make sure that that everyone's Andrew ID is appropriately attached to a team in this way, and so we'll send out instructions for just how to go about this. We had also sort of internally scheduled these sort of special office hours to just like chat about project ideas and also help people form project teams if they didn't have them. We had those scheduled for last week, but weren't quite ready to actually put them on. So we're just going to be rescheduling them to this week, and as soon as we have a room and a date and a time for those, we'll announce on Piazza. So anyway, I think there's a couple outstanding questions on Piazza. When is this actually due? It'll be due sometime soon, but it's also, if you find that you need to change teams, like as the project proposal actually lands, that's not out of the question. But we will actually have like a real submission to Gradescope just so that everybody knows how to use it. Okay, so last time we talked about Monte Carlo methods, and this time we're going to be talking about MCMC, the algorithms at the top, the Metropolis algorithm, the Metropolis-Hastings algorithm, and Gibbs sampling. We'll spend a little bit of time talking about Markov chains, and I have some extra material to talk about these last two algorithms, though we may or may not cover them, just sort of depending on time. There's a lot of things to say beyond just these basic algorithms. Okay, so we're going to start with sort of a look at the algorithms themselves, and then we'll actually come back to why it is that they actually work. So last time we left off thinking about these different inference problems for a factor graph, which are computing different sort of quantities of interest given a fully trained model. Right? And we said that for the last three, computing marginal probabilities, drawing samples from a conditional distribution, computing conditional marginal probabilities, that we could use samples to actually compute these. So what I want to do is think about sampling directly from a joint distribution. And so here, what we're looking at is just a little example akin to one that we looked at when we were first introducing Bayesian networks of an actual graphical model, as well as the conditional probability tables for that graphical model on the right. Okay, and I didn't write them out as tables per se. I wrote them out mathematically by saying that the random variable t follows a Bernoulli distribution parameterized by some parameter tau. And tau has the value 1/2. Okay, so you could think of that Bernoulli distribution as an evenly weighted coin flip. So h is also parameterized by a Bernoulli with parameter eta equal to 1/3. And then a is a Bernoulli parameterized by alpha ht. And here you should observe that the parameter for a is dependent on the value of h and t. So here we, depending on, if h is equal to 0, say, and t is equal to 0, then the parameter alpha takes value 0. So that would be like a coin where whenever you flip it, it just always comes up heads. Or sorry, I guess maybe if alpha is 0, that means it always comes up tails. And then the last variable here is just a uniform distribution over the numbers 1 to 6 plus the value of a times another uniform distribution. So if we want to draw samples from the full joint distribution of a Bayesian network, all we need to do is proceed through this generative story, line by line, and that will give us a sample. Okay, so what does that mean? Well, for sampling t, it would be like you pick up a coin and you flip it, and it comes up heads, and so we write down that t is equal to 1, and then you pick up another coin, but this time it's got weight 1/3, so this is a different coin, and you flip that one, and it comes up tails, so that's 0. Now for a, we know what h and t are. H is 0, t is 1, and so alpha needs to be the value 1/2. Okay, well, we actually already have a Bernoulli distribution parameterized by 1/2. We just used it to sample t, right? So that's just an even coin flip. Okay, so we flip that coin, and a comes up, let's say, as heads. Okay. So now we need a uniform distribution over the numbers 1 to 6. That would be like rolling a die. Okay, so it comes up 3. And then we need to roll another die, okay, because we have another uniform distribution times a. So it's going to be 3 plus a times whatever the second roll of the die comes up. Okay, so we roll the second die, it comes up 2. So 3 plus a times 2 is 5. Okay, so that's how we draw a sample from a joint distribution. This is very easy. And we could just continue drawing samples exactly in this way. You just start back at the beginning. Flip a coin, sample t, you get 0. Flip another coin, sample h, you get 1. Flip another coin for a, you get 0. Flip another coin, roll some die, say you get 2. And you could just proceed through this process, collecting examples and gathering data in this way. Okay. So what we saw last time was that you could use all of these samples to estimate different quantities, but some of those quantities you might get sort of poor estimates of. So, for example, if I wanted to estimate a marginal probability, say I wanted to estimate the probability distribution over t and h, given that a is equal to 0. Well, in this case, I actually only have one sample for which A was equal to 0. That was this one. So here, oh, sorry, and let's say maybe we condition on two things, like A equal to 0 and C equal to 2. Okay. Well, that did actually come up once, but I only have one sample from which to estimate it. Okay. There are other combinations of A and C for which I have no samples. And so in order to even see those conditional marginal distributions, we would need a lot of samples of those specific cases that we care about. Okay. So suppose, for example, you were trying to use sampling to estimate the marginals of an HMM. Okay. So you have a sentence like time flies like an arrow, and you're trying to estimate the marginal probabilities of the tags. Okay. So what I'm saying is you could draw samples in this way from the full HMM. You would draw a sample of tags and words. But if you wanted to estimate the marginal probabilities conditioned on a specific sentence, you're going to have to keep on drawing sample after sample after sample and discarding all the ones for which the sentence is not time flies like an arrow, because they don't apply to actually estimating a conditional like this. Okay, so Markov chain Monte Carlo, the goal here is to draw approximate correlated samples from a target distribution P of x. Okay, now the fact that the samples are correlated, I guess I wrote that in the goal, is not necessarily that we actually want the samples to be correlated, but any Markov chain Monte Carlo method is going to have that inherently in it. And so what it actually does is it performs this biased random walk around the distribution. And if we run it long enough, the samples that come out of it will eventually be from the true distribution, so long as we set up the Markov chain correctly. Okay, so it's useful to kind of see some picture of how these things actually work. And so what we're going to do first is a visualization of Gibbs sampling. And so you can see, if you watch carefully here, that what we're watching is basically a random walk. So it jumps to some new point at the end of the green arrow, and then it resets from that point and takes a new jump somewhere else. And so we're always taking these steps around the distribution, and if we let this thing run long enough, sorry, an important detail here is that the underlying distribution is shown by the contour plot and then also the heat map. So high probability regions are darker blue. And you can see that as it's drawing samples, we're also collecting a histogram over the different values for, say, the variable x1 and for the variable x2. And as we run this sampling process, those histograms are starting to match the true marginal distribution, which is shown as this curved line. Okay. And so if we turn up the speed, so here we have an autoplay delay of 250. So now let's get this down to no delay. You can see that as we collect more and more samples, these marginal distributions are starting to look more and more like the actual true marginal distribution. So how is it that they actually create this little histogram? Well, you can imagine just taking all of those points and projecting them directly down onto this axis, and just counting how many land in this particular bin and how many land in that particular bin, and so on. Okay. Great. So next, I want to actually look at how does this algorithm work. So let's see how it works. So Gibbs sampling it's a lovely little algorithm, and the idea is that we draw samples one variable at a time from what are called full conditionals. Which we'll define in a moment. And those full conditionals are just we always accept the next sample. Okay, so you'll remember that last time we talked about a Monte Carlo method called rejection sampling, where we would take a sample and we would either accept or reject it. So here, we're going to set things up so that we always accept the samples that we're given. Okay. So full conditionals are just conditional distributions. So for a distribution, say P of x1, x2, up to xt, we have full conditionals that are P of xi given all of the other variables except for xi. So that would be, x1, x2, up to xi minus 1, then xi plus 1, all the way up to xt. And maybe a more proper way to actually write this would be P of xi given the set of variables xj such that j is not equal I. So here's the algorithm. We're going to say let x superscript 1 be the initial state. Or rather, let me rephrase that, the initial assignment to the variables. So here, this is a vector x1 giving us a value of every single one of our random variables for the distribution. And then we're going to say while true, we're going to repeat the following. So for each of the random variables, so we could say for I equals, say 1, or let's say for little t equals 1 up to capital T. So this is for each of the random variables. We're going to sample one of the random variables. Oh, actually, sorry, let me be a little bit careful here. So I'm going to use t, so I'm going to use I to index, let me make sure I get this right. So we're going to use subscript little t to index the variables so that I can use the value I, whatever I'm referring to, say, time steps. Okay, so here I just re-indexed to t. Okay, so now what we're going to do is we're going to say sample the variable xt, and this will be superscript I plus 1 from that full conditional for that random variable. So this is going to be the probability distribution over xt given all of the other variables except for xt. So that would be xs for all s not equal to t. So we're just resampling the value of one of the variables. And we're using the values of the variables at time step I. So we're going to have some counter back here that's keeping track of our time steps, and we could initialize I to be not 0 but 1. So this is at time step 1. Okay. And then we're going to set the actual value of I to now be I equals, so let me be very careful here. So we just resampled one of the variables, but all of the other ones have stayed exactly the same. So just so that we're kind of indexing properly with time steps here, we're going to say set all of the other variables besides t at time I plus 1 to be equal to all of the variables besides t at time I. And then we can set I equal to I plus 1. So here all I'm doing is just making sure that the indexing in terms of timestamp updates every time we resample one of the variables. Okay. So this is the whole algorithm. Now let's actually look at applying this sort of general algorithm to a specific example. So our example here will be a factor graph. And we'll say that the factor graph is, pretty simple. It just consists of 3 random variables, A, B, and C. And the factors, there's one factor between each pair of random variables here. And they're labeled as, psi AB and psi AC and psi BC. And for simplicity, we're going to say that each of these random variables, A, B, and C, are labeled as either plus or minus. And we need some factors here. So let's just spell out what the actual entries in these factor tables are. So here we have psi AB. And so there's 4 different values. So there's plus plus, plus minus, minus plus, minus minus. And we're going to have values of 1, 2, 1, 1. So that's our first factor table. And then for the factor AC, here again we have 4 entries. And this is going to be all 2's except for the last one. So it's going to be 2, 2, 2, 1. And then the last factor table is for BC. So here we're going to have the values be 1, 1, 2, 1. So there's our factor tables. And the first thing that we want to think about is where we're actually going to get the full conditionals from. Okay. So the key thing that I want us to think about for this example is sort of how we can actually work with things that are proportional to the probability. So, and the sort of key observation that you need to keep in mind here is that if all we're trying to do is sample from a distribution, we only need something proportional to it. So to sample from a discrete distribution, rather, right? So some distribution, say P of y, we only need a function proportional to it. That would be like some something such that g, let's call it a function g, such that we have that the probability of y is proportional to g of y. So just so we have an example to think about here. Imagine that what we want to sample from is a distribution over 3 colors, like red, green, and blue. And you know that red, the probability of coming up red is proportional to 1, probability of green is proportional to 1, and the probability of blue is proportional to 3. So in that case, all we need to do is either take those things that are proportional to the distribution and we could just renormalize it, right? Or we could do something even simpler, which is draw some value from a uniform distribution between 0 and 1 plus 1 plus 3, which is 5. So draw some value between 0 and 5. And then in step 2, ask the question, which bin does U land in? Right? So you could think of this like, here we have these little bins, and they're spaced out according to these different values, right? So here's the bin between 0 and 1, and then this bin is from 1 to 2, and then this bin is from 2 all the way up to 5. And so if we sample between 0 and 5, that's like taking some value randomly, maybe like the value 1.8, and 1.8 lands in the bin corresponding to green, so we could return green. Okay, so with that in mind, let's go back to our factor graph here, because we can say, one of the full conditionals that we want to work with is something like P of A given B and C. So this is one of the full conditionals. And we can start by rewriting this as P of ABC divided by P of BC. Right? This is just probability. So what this means is that we have our first sort of version of something that's proportional to our original quantity, right? So we could say this holds with equality, but this thing is proportional to P of ABC. So why can we do this? Well, for this distribution, we need to make sure that the actual distribution over the A's is sort of preserved, right? So we can't leave out any terms that would affect one of the values for A. But P of BC is constant with respect to A. So if we leave it out, we still have something that preserves all of the information about the relative probabilities of A. Okay, so let's play this game again. And this time, let's say, well, this P of ABC here, we know that P of ABC is equal to, according to, let's say, we have our factor graph here, so let's assume it's a Markov random field. So it's going to be equal to 1 over Z times psi of AB times psi of AC times psi of BC. Yeah.
So shouldn't the probability of like B given AC or like C given AB be proportional to P of A, B, and C as well? So like how do we differentiate? Like all the probabilities are proportional to probability of A, B, C. So
Yes, exactly. So yeah, so what is going to be sort of different between the actual different sort of conditionals? You want to see it? So let's ask this question. How many table entries are there for this distribution? That joint probability distribution. Let me actually write it on the other side here. So number of table entries here, and number of table entries here. So how many table entries do we have for P of ABC? 8. And for P of A given BC? 2. Okay, so only 2 of those 8 joint probabilities actually come into play when determining this conditional distribution for a specific value of B and BC. Okay, so now this question is a little bit misleading, right? Because we could also say that, well, maybe this is actually a table of 8 entries, right? But only 2 of them sum up to 1 for each value of B and C. So, okay, so here's the interesting trick that we can now play. So here's our definition of P of ABC. This is how we actually define the thing. And now we can play another trick with proportionality here and say that this is further proportional to, well, only terms that actually involve A. Okay, so Z is constant with respect to A. So we don't need this term. And B and C are constant with respect to A, so we don't need that term. So all we need are psi of AB and psi of AC. Okay, so if you want to compute a full conditional for P of A given BC, you only need to multiply 2 numbers together. Okay, so let's spell out all the full conditionals here so we can see the bigger picture. So full conditionals are going to be, so there's 3 of them. There's P of A given BC. There's P of B given AC. And P of C given AB. So the first one is proportional to psi of AB times psi of AC. The second one is proportional to psi of AB and psi of BC. And the third one is proportional to psi of AC, psi of BC. Where, okay, I'm kind of getting lazy here. We should have subscripts under all of these, psi, AB, of AB, but I think you guys know what I'm talking about. So there's a couple things that we should say here. One is we're going to take each of these and we're going to call it some function of A, like a function g of A. And then this we can call some function g of B. And this is some function g of C. And you could think of these as just defining a little distribution over the possible values of A, plus, minus, right? And B, and maybe they look different, right? So maybe here, plus is pretty unlikely and minus is pretty likely. And C, where maybe it's the other way around, plus, minus. But the other thing to notice is that these functions might actually change at each iteration. Why is that? Why would the function g of A change?
If the probability distribution changes.
Well, this definition is going to stay the same. But here, g of A is like a function over plus and minus. So the actual like relative ratio of plus and minus might change from iteration to iteration. What causes that change?
There's sampling, so that you're updating.
Well, we're sampling something that changes, but what changes? Yeah.
Is it that word excluding the ith probability at every iteration?
Let me think about whether that's true. It's where it refers to one of the variables. That's not quite how I would put it, but I mean, in essence, yes. Can anyone sort of rephrase that in a different way?
Will it change based on what we sampled as B and C?
Exactly, it'll change depending on what the values of B and C are. So g of A, you have one value for g of A equals plus, g of A equals minus, but it all depends on the fixed values of B and C, right? So these values here, highlighted in blue, are essentially, they're sort of fixed while sampling. So let's actually spell out sort of the whole algorithm here just for this small example. So the algorithm is going to start, this being the Gibbs sampling algorithm, by initializing A, B, C randomly to some values in not 0, 1, but plus minus. And then from there, we're going to say for I equals 1, 2, 3, and so on, we're going to resample each of the values of the variables. So I'll say A is sampled from the distribution P of A given BC, and B is sampled from B given AC, is sampled from P of C given A, B. So now you can see how the values are showing up in these little quantities, right? We're going to be recomputing that conditional distribution, or using potentially a different conditional distribution each time. So I thought it would be useful to see just how simple this is. Oh, actually, sorry, before we get too far, we should make an important note. Just don't want to forget this. So I'm going all the way back up to our broader algorithmic definition here. And the important note is that when we're sampling from these full conditionals, it does not assume access to the partition function. For example, if P of X is defined as P tilde of X divided by Z, then we don't need the full distribution P of X. We only need P tilde of X. So this is nice, that we don't actually have to have the partition function, and we can still do this sampling. And so the reason I want to kind of call it out in the general case is now when we look back at our small example here, that's exactly what we're seeing, which is that when we defined the full conditionals, we did it without access to the partition function. Okay, so now let's actually look at an example of oh yeah, question.
Going back to the original algorithm, do we increase I within the for loop, or is I incremented after the end of the for loop?
Oh yes. So you know what? I shouldn't have even written. So I was like being too tricky for my own good in this particular definition. Let me just define it in another exactly identical but slightly different way that probably will make this clear. So this is exactly the same algorithm as above. Okay, I'm just going to write it differently. So initialize x1 here, and then we're going to say while true, or rather, let's do what I had below, which is a for loop for I equals 1, 2, 3, and so on. We're going to say for t equals 1, capital T. Oh, sorry. So the key change that I'm about to make here is I'm not going to superscript these with timestamps. So I'm going to just write this out as if we just have a single vector of variables x. So in that case, what we can do now is we can say for each variable, just resample the variable xt to be a sample from p of xt given the set xs s not equals t. So what I've done here is I've just said at each time step, you're updating one of the variables. Just resample one of the values, and then you just move on to the next variable. Resample that value. But you update it, you can imagine X here is just like a vector of values. You're just updating one entry in that vector at a time.
So the full conditionals remain the same for one iteration of I, or are they also updated every two?
So technically, these full conditionals are fixed, except that, like, if you wanted to, you could pre-compute all possible full conditionals, right? And
But
all of those values, or something proportional to all possible full conditionals. But in practice, you probably don't need to, because you might never observe all of the things, the possible configurations of variables you're conditioning on.
Right, but once we sample XT, right, then the number of times we observe a particular XT changes, right? So the full conditional should change in accordance with that.
No, so the probability distribution is not changing. The only thing that we're doing is we're using a different sort of particular probability from that model. So the value of xt in this right-hand side can change, but the actual distribution itself is remaining constant. So it's just which full conditional are we looking up? Okay, so let me actually let me preview something. I was gonna show this sort of afterwards, but I think this is like exactly the right moment to see this. So for graphical models, the full conditional only needs to condition on the Markov blanket. Okay, so when we're working with Gibbs samplers, if you want the probability of some variable like x6 conditioned on all of the other ones, the graphical model tells us that that is equal to the probability of x6 conditioned on its Markov blanket. That's one of the first independence properties that we came up with for these things. Right? And the same thing goes for an undirected or a directed graphical model or a factor graph. And the point is just which of the variables are actually in the Markov blanket. Okay, so this is critically important because if you think about, how many actual entries in the full conditionals, if you spelled them all out without conditioning on just the Markov blanket, say we had 100 binary random variables. Okay, well then if you spelled out all of the possible full conditional values, that's a table of 2 to the 100th values. Okay, but we're only going to compute the ones that we need on the fly with the actual Markov blankets. So this is sort of the key thing here is just that like those probability distributions are fixed, but how we're using them is changing from iteration to iteration. Okay. So now let's actually implement Gibbs. Oh yeah, questions.
Yeah. So the p tilde x we have here is the same as the p star x that we had in importance in direction sampling. It's still the same topic.
Oh yeah. What notation did I use for? Did I use?
I don't know. It was either p star or p tilde in importance in direction, but it's the same thing. Right?
Yep. Yep.
But over there we did define any concept of full conditionals. We just had some p star x.
That's right. So the difference is that a full conditional is the probability of one variable conditioned on all of the others.
Right. So over here, evaluating p tilde x makes sense, and why it's computationally less intensive, it makes sense. But over there, what was p star x then, and how were we evaluating p star x? And how is that less intensive than evaluating p?
Oh, because so here, so I guess what I'm saying is that if you can sample from p tilde, then like if you had sort of full conditionals of p tilde, that would be sufficient to get you back samples from p.
Right.
And but then like this is even more relaxed because here we're going to have some graphical model from which we well, okay. So in its most general form, the point is just that you can compute. Sorry. So I guess we need to maybe spell this out. So to prove that you only need p tilde is just a short exercise, right? So if you want to draw samples from p of x, then, or sorry, from a conditional of p of x, like p of xt given xs s not equal to t, then that's proportional to p tilde of x1 up to xt. That's the key point. So this full conditional is proportional to the joint in this unnormalized p tilde. Okay. And then further, so this is like two great ideas. So idea one, and idea two is we might need even less than p tilde if we can rely on a Markov blanket. Just a Markov blanket. So the way that we spelled out Gibbs sampling here was technically nothing to do with a graphical model, right? We said you just have to have some way of sampling from these full conditionals. And in the most general sense, if you know how to evaluate something proportional to the joint, then that is enough information that you can sample from this full conditional. But better yet, if you know that you can just sort of relax that to just a Markov blanket, then you're in really great shape. Okay, so can we, is that?
No, so what I was asking was over here, I can see how p tilde decomposes into a product of potentials of the Markov blanket,
Yeah.
which makes sense. But over there in important rejection sampling, we didn't really discuss the form of p tilde x. We just assumed that there exists some p tilde x, but how do we get that p tilde x in that scenario is what I didn't understand.
Oh, sorry. Okay, just multiply all the factors together. Multiply all the potential functions together without dividing by the partition function.
Okay, so we still need access to all the potential functions.
Yep. That's one example. There might be other distributions where, like say, yeah, but I mean that's basically it. Just multiplying all the potential functions together and not dividing by the partition function, which is generally like the hard thing to compute. So
I remember reading in one of the readings that the only reading that we had, that there are two reasons why we calculate p tilde x. One was that it's difficult to calculate the partition function, and the other was because p of x is in a very high dimensional space. So we calculate p star of x or p tilde of x, which is in a lower dimensional space. But if we just multiply all the potential functions, then the dimensionality remains the same for the distribution study.
but think so. But I mean, multiplying all the potential functions together is still linear in the number of variables. So even if it's high dimensional, the actual act of multiplying the potential functions together is always like an easy computation. Yeah. So if I'm still not answering your question, let's chat offline. Okay. So what I want to show is how we could actually run Gibbs sampling on this factor graph. So here we have some code to do that, and let's actually just open up the code over here. So this is the code, and the first function up here to note is This is called Windows. I don't ever use it except here. That's why it's not odd colors. Really? There's not like a... No. Okay, that's not going to be easy, I don't think. No. Okay. All right. So we'll look at the slide, and so here at the top we have this function that's just sampling from an unnormalized distribution, right? So G0 is proportional to the probability of coming up heads, and G1 is proportional to the probability of coming up tails. So we're just drawing a random number from a uniform distribution from 0 to the sum of those two numbers, and then we're saying if U is less than G0, return 0. Okay, so Gibbs sampling, we need a factor graph. So we can define the factor graph with psi AB, psi AC, psi BC, and those are just little NumPy arrays where I've indexed them so that the first index is going to be, say, for psi AB, the first index is going to be the value of A, and the second index is going to be the value of B. And for psi BC, the first index is the value of B, and the second index is the value of C. And these are the same. This is the same factor graph that we just wrote down. And so we need to randomly initialize the variable values. Okay, so random.choice just takes a list of options, like plus minus, and it selects either plus or minus randomly. Okay. So here I encoded plus and minus as 0 and 1. And now I have this counts variable that we're going to use to count up the number of times that we see each variable assigned to a particular value. Okay, so that's all this is going to do. So we initialize those counts to 0. And so here you could think of this as like, this is, so this is going to give us the number of times that A is equal to 0, and this is the number of times that A is equal to 1. And then here, this is the number of times that B is equal to 0. And this is the number of times that B is equal to 1. Right. Okay, so now let's actually do, and so on for C. So now let's actually do our sampling. Okay, so I is just iterating over time steps, right? How many times am I actually going to sample all these? So we've already assigned values to A, B, and C, and now we're going to say resample the value of A. Okay? So to do that, I need two numbers. One is a quantity that's proportional to the probability of A equaling 0, and the other is a quantity that's proportional to the probability of A equaling 1. Okay? Those numbers are really simple to get, right? It's just the two factors that participate. So psi AB for 0 and whatever the current value of B is, times psi AC of 0 and whatever the current value of C is. And then the same thing for psi AB with A equals 1 and psi AC with A equals 1. Okay. So all we're doing here is resampling A, and then resampling B, and then resampling C. And then we just print out whatever the values of A, B, and C are after we resampled them all. And then here, I'm counting up the values of A, B, and C. Okay. So now, there's sort of an interesting question here, which is how many samples are we actually getting out of this run? Okay, so the way that I set it up, we're getting out 10 samples, right? At the end of it, of resampling A and B and C, I get one sample, and I count up, I increment, the value of A and the value of B and the value of C for that particular sample, and I print out that sample. Okay, but I could have taken these 4 lines, printing out the sample, aggregating the counts, and injected them in between resampling of A and B and resampling B and C, such that we would effectively get back 30 samples, right? One after each call to sample 0, 1. Okay. So this was just a design decision, and doesn't really make a big difference here. And then at the very end, I'm just going to print out our estimate of the marginal probability of A, B, and C. And we do that just by looking at those counts of counting up. How many times did A equal some value, B equal some value, and C equal some value? Okay, so now let's go ahead and run this. Okay. So it drew 10 samples, or 10 that we kept track of, and it estimated P of A equals 0 as 80%, B equals 0 as 30%, and C equals 0 as 40%. Where I'm assuming you can figure out that P of A equals 1 was 20%. 1 minus P of A equals 0. Okay. So that's nice, but 10 samples isn't very much. So why don't we sort of turn up the number of samples here. So rather than 10, let's say we're going to do 100 samples. So we run this again, prints out all of our samples, and then now it's getting 0.67, 0.3, and 0.63. Okay, that still feels like a little small. Why don't we multiply that by 100? Now we're taking 10,000 samples. And we'll sit here for a little bit. Printing is the thing that's taking the majority of the time here. If we weren't printing this out, it probably would have been done long ago. Here we are. On a Mac, somehow this printing didn't take very long. So maybe the Mac terminal is like doing better buffering or something. I don't know. Okay, maybe we'll kill this and comment out the print loop. I guess we could also just come back and check on it in a little bit. Okay, so let's look at some more examples of Gibbs sampling, and then we'll come back and see what our estimates of the Markovs were. So this is just sort of a picture of the original little web browser demo of Gibbs sampling that I showed you. Right? What was going on there was that we had some initial values for x1 and x2, right? So here's some xt, this is a vector, right? And it has some value, t here is indexing the timestamp. So this is like x1 t, and the value here would be x2 t. Okay. And if we took some full conditional as just a distribution over x1 conditioned on x2, okay, now you can sort of see why we wouldn't want to store all of the possible full conditionals. Because here, x2 is now a real number, and so the actual distribution over x1 is really like a slice of this two-dimensional distribution. Right? And so when you compute that full conditional, you really want to do it for the current value of x2. So compute it, use it, and then probably discard it. Okay, so we get this distribution, and then we randomly sample from this distribution. And let's assume that you already know how to do that by either some efficient method or some Monte Carlo method. But somehow it's pretty easy because it's just a one-dimensional sample. And you get some new sample. That's xt plus 1. Okay, so now you move there. This is your current sample. And now you get a new distribution over x2. And you sample a new value of x2. That gives you a new sample, xt plus 2. Okay, and you move there. And now you get another full conditional to sample another point, and you just gradually move around this space. Okay, so we can use Gibbs sampling to draw samples from a conditional distribution, like a, say, conditional random field. If we sort of say, okay, well, we have a bunch of variables these x's that we want to condition on. And what we're trying to do is just take samples of the y's conditioned on the x's. So we can initialize the values of the y's to some arbitrary values. And then for time steps t equals 1, 2, and so on, we're going to draw these samples from the full conditionals. Okay, so here the way that I indexed time steps was to say that a sample is like a full collection of all the variables. And so we see that the full conditional for y1 is just conditioning on all of the x's and all of the y's except for y1. And then the full conditional for y2 is again conditioned on all the x's and everything except for y2. Okay, and so on down the line. And so if we run this long enough, it will eventually yield samples from the true distribution that we care about. Okay, let's see if this thing stopped. Oh, it did. And you can see that what it seems to be converging to is that the probability of A equaling 0 is about 2/3, the probability of B equaling 0 is about 1/3, and the probability of B equaling 0 is about 2/3. So basically it wants A and C to be equal to 0, and B it wants to be equal to 1. So let's actually look back at our factor graph, and we can see that the actual way that I encoded those plus minuses, I think, was plus is 0 and minus is 1. So here, the factor for AB is saying, I really like A to be a 0. And the factor for BC is saying, I really like C to be 0. And then the AC factor is basically saying, I don't really care. Oh wait, sorry, did I read that wrong? Yeah, so A and C. So it just really doesn't want them both to be minus minus. Okay, and I guess for B, both of the first and the last factor, those 2's are cases where B is equal to minus, which is 1. So you can kind of see, like, just even by looking at this particularly tiny example, you can kind of guess what those marginals would have been. And the sampler did actually get it right. Okay, so in general, when we're working with these factor graphs, we don't just have 3 variables. We actually have a bunch of variables, and we only condition on the ones that are actually in the Markov blanket. And we only need to multiply together the factors that involve the Markov blanket. Okay, so now we're going to talk about a slightly different algorithm called the Metropolis-Hastings algorithm. And to get there, we're going to first talk about the Metropolis algorithm. Okay. So the Metropolis algorithm we're going to say that like importance and rejection sampling, we're going to have a proposal distribution, but the form of the proposal distribution is going to be quite different. So we're going to choose a proposal, and that proposal distribution is going to be a distribution over the vector x conditioned on a vector x prime. And we're going to choose that proposal such that Q of x given x prime is equal to Q of x prime given x. Okay. what this means is just that the actual proposal distribution is what we would call symmetric. So the proposal distribution, what it's going to be used for, is we're going to condition on the current sample to give us a proposal for a new sample. Okay, so that's why it's the full vector x. Okay, so like before, we're going to choose an initial state, and this is going to be some vector x1. And now we'll say for time steps I equals 1, 2, 3, and so on, we're going to, I guess we could have numbered these so we can actually refer to them. So step 1, step 2, step 3, and then we'll have step 3a. In step 3a, we're going to propose a new state. And that new state is going to be some vector x sampled from q of x given the x at time t. Now, that x doesn't automatically become our next sample. Instead, step B here, we're going to accept that newly proposed state x with probability of a, where this little a is it's a value between 0 and 1. Okay. So this is going to be a coin flip. And we're going to say that this acceptance probability, we'll talk about it as some capital A of getting this new sample x from xt. So we're just kind of giving it this fancy capital A name so that we can actually refer to it in the next algorithm. And we're going to define this to be the minimum of two quantities, 1 and p tilde of x divided by p tilde of xt.
Is D supposed to be I?
Oh, whoops. Yep. So here we have I, and here as well we have I. Thanks for catching that. And then this is also I. Yeah, so we're iterating through I. And then we'll say that step C, so if that vector x is accepted, then we set the value of x at time I plus 1 to be equal to x. Otherwise, we set x at time I plus 1 equal to the current x at time I. So this is really sort of a definition of what it means to accept a sample, is that we're going to carry it on. We'll actually like move to that as our sort of new state. Okay. So when we say that, if x is accepted, what we're really saying is we want to know whether that quantity A is greater than some u when sampled from a uniform distribution in the range 0 to 1. So if you sample a value between 0 and 1, and A is greater than U, then we accept. Okay. So it's like flipping a weighted coin with weight A. Okay. So, so this is the Metropolis algorithm. And now, given this Metropolis algorithm, we're going to define one more algorithm, which is the Metropolis-Hastings algorithm. And here, we're just going to take the Metropolis algorithm as is, and we're going to make a small tweak to it. Okay. So the proposal, Q, doesn't need to be symmetric. So for the Metropolis-Hastings algorithm. Okay. So this algorithm is identical to the Metropolis algorithm, except there's one change, which is that we accept with probability that's slightly different. So here, the acceptance probability is A of x from x at time I, and we define this to be the min of 1, and here we're now going to do something that kind of looks like importance sampling. So what we're going to do is we're going to say, we're going to take p tilde of x and divide by p tilde of xi. But then we're going to scale this thing by our proposal distribution. So in the numerator, we'll have q of xi given x. And in the denominator, we'll have q of x given xi. So basically what we're doing here is we're saying that the Metropolis algorithm is just a special case of the Metropolis-Hastings algorithm with Q being symmetric. So in fact, if you kind of jump back up here and think about replacing that acceptance probability with our definition down here, if Q is symmetric, then we have that this quantity is equal to that quantity. So this is just like multiplying by 1. So what we're doing in Metropolis-Hastings is a little bit different from Gibbs sampling, because we actually have to have this proposal distribution, and we propose some new state, and then we only accept it with some probability. The interesting bit is that it turns out that Gibbs sampling is a special case of the Metropolis-Hastings algorithm. So how is this possible, that Gibbs sampling could be a special case of Metropolis-Hastings? Because it feels like, Metropolis-Hastings, you make a proposal and then you're going to flip a coin to accept or not accept. Okay, well, Gibbs sampling, we'll see next time, that you can set things up so that the proposal distribution for Gibbs sampling is just sampling from a full conditional. And the acceptance probability for that specific proposal distribution is always going to be 1. We're always going to accept the proposal from the full conditional. Okay, so we'll be able to see that the Gibbs sampling algorithm is a special case of Metropolis Hastings. And then in addition, we'll see that there are properties of the Metropolis Hastings algorithm that ensure, regardless of what the proposal distribution is, that if we run it long enough, we should eventually get samples from the distribution that we want. Okay, and so that will kind of conclude our look at these Markov chain Monte Carlo methods. Okay, so we'll see you guys on Wednesday.